Okay, for our first spotlight problem, we're going to be looking at this one, which is x prime equals x minus 4. These are relatively complex problems because what we want to do is look at the critical points, and then we want to look at the solution and the slope field to see why, in fact, the critical points behave in the way that they do. And remember, critical points are points that the function is either going to flee from or converge towards as t goes to infinity. So first thing we want to do is find the critical points. Critical points will occur wherever the slope is 0. So we do it by setting the right-hand side equal to 0. So these are always in the form of x prime equals some function of x, f of x. And what we want to do is set f of x equal to 0. In this case, we can see that means x equals 4. So x equals 4 is a critical point. It's going to represent one of these horizontal lines in the slope field where the solutions either go to 4 or flee from 4 as t goes to infinity. To see which one, we're going to test the nature of the slope on either side of 4. So what I want to do is take x prime of a number just below 4, which would be 3.9. Now, any number will do. I'm just picking 3.9 because it's below 4, okay? Now what we do is we look at the function value, x minus 4. So that's going to be 3.9 minus 4. I don't really care what the function value is. I just want to recognize that this is negative. So because it's negative, it means the slope is negative when we're below 4. And if we think about it, what does a negative slope look like? Well, a negative slope slopes down and to the right. So as things are increasing or going further to the right, we're getting closer and closer to the critical point. So that gives me information that when we're below 4, we're going to be moving towards the critical point. Oh, excuse me, when we're below it, 3.9 is below it. When we're below it, we're negative, so we're going to be moving away from it, okay? Now let's check the other side, when x prime of 4.1. Okay, so when we're at 4.1, we can see that the function value now is going to be 4.1 minus 4. And again, I don't really care what it is, I just know that it's a positive number. And that means the slope is positive when I'm above 4. So if the slope is positive when I'm above 4, it means it's moving up and to the right. So as t goes larger, we're going to be getting further from 4. So a way to sketch or construct this is I can just draw a number line. And on that number line, I can put the number 4. And then I can indicate what the function's behavior is around that. If I'm below 4, then I'm getting more negative. And if I'm above 4, I'm getting more positive. And what this tells me is the behavior in the slope field is that around 4, the function is fleeing from 4. This is classic unstable behavior. Okay, now let's solve the differential equation and see what we end up with when we find the solution. So this one's not too bad to solve. When I take this guy and separate it, I'm going to get dx over x minus 4 is equal to dt. And of course, integrating is going to give me the natural log of x minus 4 is equal to t plus c. Or taking the exponential of each side, that x minus 4 is actually equal to c e to the t. And of course, that's going to result in that x is equal to c e to the t plus 4. And we can see what this sort of behaves as. That is c e to the t as t gets more positive, increases and moves up higher and higher. So this will be a horizontal line at 4. The equilibrium position will be when the slope is 0, but it'll move up when we're above it. And then we know right here it'll move down when we're below it. If we look at the slope field of the original function, and that'll be coming up right after this, we can see the role of these solutions play within that slope field. Okay, so here's the function plot with the slope field for this first problem, x prime equals x minus 4. So here it is programmed in. There's the slope field. And we had indicated that at 4, which is this horizontal line right here, that this would be an unstable equilibrium. And you can see why by the slope field. As t advances to the right, if you are on the equilibrium, you're eventually going to leave. And here's all the solutions. Like, even though we can get it to lie on 4 for a while, at some point it's going to bounce off. There's really only one solution, the trivial one, where y does equal 4, and then the slope is 0, and it sits right here. But if we have any initial condition that lies anywhere off axis, then it's eventually going to leave the equilibrium position and, of course, head up to positive infinity or negative infinity as t increases. So this is the essence of what an unstable equilibrium looks like. Okay, here's our second spotlight problem, and we're going to do the same thing with this one we did to the last one. It's a little bit more complex because it's quadratic in nature, but we want to do the same thing. Because it's x prime equals some function of x, we want to set that function of x equal to 0 and see where the critical points are, the places where the slope goes to 0. So we can see this one's pretty easy. X will equal 0 at 0, so f of x will be 0 when x equals 0 and when x equals 1. So those are our two critical points. And just like we did before, we're interested in the behavior of the slope right before and right after the critical point, so we can see whether it's trending towards or away from the equilibrium line. So I want to find x prime of some number less than 0. It doesn't really matter what it is, so I'm going to say -1. That's below 0. So x prime of -1 is going to be 3 times -1. And then 1 minus a -1, or 1 plus 1. So this is going to be a negative number. It doesn't matter what its magnitude is, it's going to be negative. So once again, when we're below 0, we're going to have a negative slope. And that means as we're approaching this critical point, we're going to be doing so by trending away from it because we're below it and we have a negative slope. This looks like it's an unstable equilibrium point, but let's check the other side. So x prime, we can't use 1 because that's the other critical point, so I'll use 1/2. And that will be above 0, but it won't be at the other critical point. So when it's 1/2, this is 3 times 1/2. And then 1 minus 1/2 is also 1/2. So it doesn't really matter what the value is, it's positive. And because it's positive, when we're slightly above the critical point of 0, we're trending away from it because we're above it and we have a positive slope. So this right here, the equilibrium point at 0 is unstable. Okay, now let's check the other critical point, 1. So we want x prime of something less than 1. Well, we can just use the 1/2. That's positive because 1/2 is also slightly below 1. So we know we're positive when we're below it. And if we're below it and positive as a slope, that means we're moving towards it. So that indicates that maybe the critical point at 1 is stable. But let's check the other side. So again, any point above 1 will do. So let's just go 1.1. And x prime of 1.1 is going to be 3 times 1.1, and then times 1 minus 1.1. And of course, 1 minus 1.1 is going to be a negative number, so the whole thing's going to be negative. Doesn't really matter what it is, it will be negative. Which means if we're below the critical point, above the critical point, we have a negative slope, so we're moving towards it. And so that clinches the deal. At 1, we've got a stable equilibrium. And we can show that with a number line where we graph 0 and 1. And we know that around 0, if we're below it, we're going negative. And if we're above it, we're going positive. And if we're below 1, we're going positive. And if we're above it, we're going negative. And right there we can see that the functions on the slope field are going to trend away from 0, but towards 1. And so we'll see that when we see the actual slope field itself. First, though, let's see what function we'll see in the slope field, and that means actually solving this differential equation. This one's more challenging than before because, of course, it's going to require us to do partial fraction decomposition because the diff EQ is going to be dx over x times 1 minus x, and then on the other side it's going to be 3 times dt. I don't like this 1 minus x. I want it to be an x minus 1, so I'm going to add an extra negative. So when I do the partial fraction decomposition, it's really -1 over x times x minus 1. You're allowed to do that. And then over here, we can actually go a over x plus b over x minus 1. And it represents the same thing. It's just I'll have to remember when I'm doing the the integral, that this is really negative dx. So there'll be an extra negative in here because the original equation was this, and I've changed it to this. So there's an extra negative in here. Let's look at what a and b then would be when we do this decomposition. So again, this means taking ax minus 1 plus bx when I rationalize or make the denominators common. And now I can see that negative a is going to be the only constant on this side, and that equals negative 1. So if negative a equals negative 1, then a equals 1. And if a equals 1 and ax plus bx equals 0, then b equals negative 1. And so now I can do the new function. This function is the same as this function. Again, I need the extra negative in it because this wasn't the original function, this was it. So I've added in that negative, and that's formed the new a and b for me. So this guy will then equal 1 over x minus 1 over x minus 1. And we've done enough of these to know, you know, these are dx and dx, and this is 3 dt. So we can go pretty quick to the solution. It'll be this over this. So x over x minus 1, and that's going to be equal to, by the time I'm done with this, this is going to be c e to the 3t. And then we can rearrange this. Ultimately, it's going to produce, once it's all rearranged, it's going to produce that x of t is equal to c e to the 3t divided by c e to the 3t minus 1. And that's just rearranging this to solve it explicitly for x of t. Okay, now let's see what this guy looks like. As I said, we're expecting that the slope field is going to point away from 0 and towards 1, and our specific solutions will either be trapped in between, going from 0 to 1, or they'll be going down to 1 or away from 0. So let's see if that's what happens. Okay, here's the second example problem. In this one, we had critical points at both 1 and 0. The critical point at 1 was stable, and we can see that because the family of curves, no matter where I go, we always end up trending to 1. If we actually started on 1, of course, we'll have a stable equilibrium there, but you can see how hard it is to actually get it right on there. The initial condition has to be such that the slope is 0 for all time. Any other initial condition, and you can see if we're below it or above it, we're always going to trend to 1 as t goes to infinity, all right? Okay, the second critical point, though, was 0, and here we see another unstable equilibrium like the last one. If I'm in between here, we can see that while we'll be on that 0 equilibrium, we're eventually going to leave it as long as the conditions are such that we aren't right on 0 for all time. If we're slightly above it, we're going to trend to the second equilibrium position, the stable one at 1. So all the functions in between look like this. And if we're below it, again, it looks like a classic unstable equilibrium. At some point, we're going to leave that line and trail off to negative infinity, all right? So there it is. In this case, we have a mixture of a stable equilibrium and an unstable equilibrium, producing a family of curves that trend downward below. In between, they trend from lower to upper, and on the top, they trend down to the upper.